Okay, I think that'll about do it. This is my talk on new techniques in repacking monorepos. We have a ton of information that I want to get through today and not a ton of time to do it. I am also the only thing standing between you and the next break, so let's dive right in. As PJ mentioned, my name's Taylor. I'm a principal engineer at GitHub. And at GitHub, I work on a handful of different things. I spend a lot of my time on the open source Git project. There I serve on the project leadership committee where I help manage the project's finances and trademarks. And I try to, at GitHub, really help teams leverage the performance of Git in various ways. I look for teams that can benefit from new ways of using GitHub, but mostly at GitHub I focus on scaling repository object storage and maintenance, and that's what I want to talk about today. This is actually somehow my third talk on scaling repository maintenance at Git Merges over the years. And to set the stage for today, I want to talk about just sort of a very brief recap of the two previous talks I've given on this subject to sort of contextualize the new things we're going to talk about today. So we'll start by talking about what GitHub's maintenance strategy looked like prior to, say, about 2020. And we'll talk about some scaling bottlenecks that we found as a result of that strategy. We're then going to do a pretty whirlwind tour of how we solved a lot of those problems with new tools like geometric repacking, multi-pack bitmaps, and much more. These tools have gotten us to where we are today. In fact, they're what are running repository maintenance on GitHub right now. But they're not without their own challenges, and that's what I want to talk about for the majority of my time today. Like I said, we're going to spend most of our time talking about some new things I've been working on for about the past year or so. And the overarching theme of that work is transitioning from this idea of geometric repacking to incremental repacking. And if neither of those terms made much sense to you, don't worry, we'll spend tons of time talking about both of them. The goal, ultimately here with this work, is to produce a repacking strategy that never explicitly repacks your entire repository into one. So we want a repacking strategy that works really well on tiny repos or medium repos, and we want it to work equally well on gigantic repos, maybe even order of magnitude larger than what we're storing today. So let's start with legacy repository maintenance. Some background here. Every time you push to a repository on GitHub, we create one new pack representing the contents of that push. And as more and more packs accumulate in your repository, the performance will tend to degrade over time as a result of having to look up objects across many individual packs, and that can slow down overall repository performance. So the challenge we faced here is how do we maintain really good repository performance even when the number of packs in your repo is growing over time? And to accomplish this, we used what I think is sort of a really simple and natural repacking strategy that I'm going to refer to here today as all into one. And the idea is that we have one really big pack in your repo at any given time. Here, I've demonstrated it as pack all. And then we have some smaller packs that are overlaid on top. Those represent the pushes that added data to your repository since the last maintenance run. Whenever we need to run maintenance to compact the size of your repository, we'll create a new pack. Here I'm calling it pack all prime. And that's going to look substantially similar to the pack all that we had in the repository at the start of maintenance, but it'll just be amended with whatever objects were added to the repo since the last time it ran maintenance. So why do something like this? For one, having fewer pack files means individual objects can be located much more quickly than they would be if they were spread across many tiny pack files. Looking up an object within a pack is a traditional binary search, and so having just one large set of data to do a binary search over is often much more efficient than doing repeated, even small binary searches across many packs. There are a couple of other reasons that you want to have objects condensed into a few or a small number of packs. One of those is an optimization that Git calls verbatim pack reuse. So this is a really critical optimization to GitHub in our ability to serve fetches and clones efficiently. Verbatim pack reuse allows Git to recognize when a portion of the pack that it wants to send you as part of a fetch or clone already appears or very closely resembles some portion of a pack file that it already has on disk. When Git determines that this situation has taken place, we can effectively stream you those bytes directly off of disk over the wire without having to actually open up and parse individual objects, and that can often result in a meaningful speedup. Most importantly though, having objects in a single pack allows us to take advantage of a really important tool that we'll talk about a lot today, which are reachability bitmaps. Reachability bitmaps store information about which objects in your repository are reachable from different commits. So having this information allows us to really quickly compute the set of objects to send, say, during a clone or a fetch, without having to actually traverse through your entire repository. You can think of an individual bitmap as being tied to some commit. Each bit position represents one object in your repository, and whether or not the bit is set to 0 or 1 indicates whether or not that object might be reached from the commit corresponding to that bitmap. So you can imagine these things combine in natural ways, like if you want to serve a clone, you can OR together a bunch of bitmaps representing the branches and tags in your repository. If you want to serve a fetch, you can OR together all the things you do want to send and take out all the things that you know the client already has, so on and so forth. But prior to 2020 or so, these bitmaps could only ever cover objects in a single pack. So if you want to cover a substantial portion of your repository with reachability bitmaps, we had to have everything down into a single pack. So as you can imagine, this strategy came with some bottlenecks. First, generating a large pack can be really CPU and IO intensive, especially for large repositories. And that often caused us to run into our sort of own self-imposed timeouts, especially on larger repositories. And this can be a real challenge for us because when a repository fails maintenance, its performance degrades further, and so it makes it harder to run maintenance in the future, which can often lead to these sort of maintenance death spirals. In fact, I remember one of the first times that I thought about this problem, I was at a team offsite in Washington, D.C. many years ago, and we were having dinner, all sitting around enjoying our time together as a team, when I learned that the kernel repository had failed maintenance, and we ended up spending most of that dinner with our laptops out at the table, trying desperately to get it to work again. And so we really want to avoid these death spirals where we can. And so to address these and a lot of the other problems that we faced, some of my colleagues and I worked on a set of techniques that I'm going to call geometric repacking. I've given a sort of extensive talk on geometric repacking and multi-pack bitmaps and things like that, so I'm going to just breeze through this very quickly, and I'll refer you back to some of the other talks I've given at Git Merge if you're interested in more of the details. So the goal of geometric repacking is to, instead of producing one single pack at the end of a repository maintenance, we're going to produce a set of packs with this property that each pack has at least twice as many objects as the next largest pack in the sequence. Here's a little example with 6 packs. I've ordered them left to right in ascending order by object count. You can see that denoted as the number in the middle of each pack. And in order to do a geometric repack, we sort of slide this cursor down from the right down to the left, checking whether or not we meet this geometric condition as we go. And so here we do that right until we get to this spot when we have 2 packs that each contain one object. It's a little contrived, but for our example it works. And that violates the geometric repacking condition. 1 is not twice the size of 1. And so we know that we're going to have to at least repack those 2 together in order to restore the geometric progression. So we start then moving our cursor back towards the right by checking, does the combined or aggregated size of the packs to the left of the cursor satisfy the geometric condition with respect to the pack to the immediate right of the cursor. And here it does, so we're done. The resulting pack structure is this. So here you can see we reused 4 of the 6 packs that we started with. So we tried to minimize our repacking effort where we could, and we wrote 1 new pack containing 2 objects. So now that we have multiple packs after repacking, there are a few problems that we have to go and solve. First, we have to ensure that object lookups remain really fast despite having objects spread across multiple pack files. We also have to make sure that we can really quickly compute the answer to reachability queries like we did with reachability bitmaps, even when those objects, again, are split over multiple packs. And we have to figure out a way to perform verbatim pack reuse in that same setting. So to address these problems, we turn to multi-pack indexes, or MIDXs, as I'll call them frequently, for short. A MIDX is a collection of objects spread across multiple packs, and the MIDX records information about each of those objects, like in what pack they appear and where within the pack that you can locate them. You can think of a multi-pack index like what it's named as. It's the sort of multi-pack analog of a single pack index. It allows us to keep our object lookups really fast, and it also allows us, really importantly, to define a sort of ordering of objects among multiple packs that enabled us to extend reachability bitmaps to cover the objects when they are spread across more than one pack. We used a similar optimization to enable verbatim pack reuse over multiple packs. Whenever you clone or fetch from GitHub today, at the very end you'll see a counter that says pack reused from some number of packs. Whenever that number is greater than 1, that's multi-pack reuse working. My talk, like I mentioned earlier, at Git Merge last year called Scaling Git covers a lot of the details if you're interested in more of that. And there are lots of other details that I'm going to skip over here as well, like single and multi-pack reverse indexes, cruft packs, and much more. Again, some of the previous talks I've given can cover that in more detail. So let's recap sort of where we are today and how maintenance currently works. We had this problem of object lookup performance. And so prior to 2020, the only way to ensure we had fast, reliable object lookup speed was to compact everything into a single pack. But today, with multi-pack indexes, we can spread our objects across as many packs as we want and generally have really fast lookup performance via the multi-pack index. For reachability bitmaps, the single pack case forced us to put all of our repositories objects into one single pack in order to cover them with bitmaps. But in the multi-pack world, we have more flexibility with how we lay objects out, and we can still cover them with bitmaps. Finally, for pack reuse, in a single pack world, we could only do the pack reuse optimization when objects were aggregated together in a single pack. But multi-pack verbatim reuse allows us to perform that same reuse technique over as many packs as we want, as long as they're stored in a MIDX and there's a corresponding bitmap. So that basically brings us to sort of where we are today. What GitHub does today is what I'm going to refer to as a sort of two-tiered maintenance strategy. We have N, where you can think of N as something like 32, fast maintenance operations, and all we do here is we do a geometric repack of every pack in your repository, and then we write a new multi-pack index containing the result. At the end of that cycle, we want to condense everything down into one pack, and that is the sort of same classic all-into-one repack strategy that we talked about at the beginning of the presentation. And so this maintenance strategy has gotten us really far. It's been running in production for about 5 or so years, but it's not without its own problems, and especially as we see more and larger repositories continuing to accelerate in their size. I've been thinking a lot about these problems and how we can ensure our maintenance strategy continues to support repositories that are going to grow much larger in the future. So one problem that we have with the repacking strategy today is that MIDX updates are quadratic. Every time we want to run a sort of update to the MIDX, we have to rewrite it from scratch. There's no way to incrementally alter or modify the contents of a MIDX. On most repositories, not a huge deal, but for exceptionally large ones, this can cause a headache, because if we want to add even a small amount of data, maybe some new objects across like 5 or so packs, if you have a gigantic repository with many millions of objects, that update can be really expensive. It's much more proportional to the size of the total repository than it is to the update. We also have the issue of the all-into-one maintenance problem. So we still, at the end of this cycle, have to compact your entire repository into a single pack. That has all the same issues as the all-into-one repacking strategy that we started with. And so GitHub still sees those issues today. We see them much less often because they're interspersed among these many fast geometric repacks, but this is still something that we deal with today. And so where I want to spend most of our time today is talking about some new work that myself and a few others in this room have been thinking about for the past year or so to address a lot of these challenges and develop a maintenance strategy that's going to scale up to the largest repositories in the world and many orders of magnitude larger than what we can work with today. And I'm calling this work incremental MIDX bitmaps, and I'm excited to sort of tell you about what that means. So to explain what this is, let's first consider this illustration of a MIDX. Here I've drawn a little rectangle at the bottom right of the screen. It has some packs in it and a little bitmap corresponding to it. And right now the only way I can update this multi-pack index is to rewrite it. But what if we allowed multiple independent multi-pack indexes to refer to each other via some sort of ordering? Here you can see I've drawn a little box, and what I'm going to do with incremental MIDXs is allow multiple layers to refer to each other through this sort of multi-pack index chain. So we have multiple MIDX layers. There's an auxiliary file that describes the ordering which you're supposed to interpret these things in, and you can sort of conceptually treat them like you have one gigantic MIDX in your repository, despite them actually being laid out over several individual layers. And you can do this as many times as you want. You can create MIDX layers that span any amount of packs, and you can create MIDX chains that span any number of layers. So what does this buy us? It buys us, at maintenance time, we can store information about objects in packs in the MIDX by adding a layer without having to rewrite the entire thing. MIDX layers are disjoint with respect to their objects and packs, so no individual MIDX layer will describe the same object twice, and nor will any object or pack be duplicated across multiple layers. And that last point is really important because it means that we can refer to bitmaps from earlier layers in later ones without having to actually reinterpret the bits along the way. New layers can write bitmaps that reference older objects, and we can combine bitmaps across layers without having to reinterpret which bits correspond to which objects. So here's a little example of that. Here I have a bitmap that we can imagine as sort of corresponding to the earliest or oldest MIDX layer. And I've drawn some bits here. They represent whether or not some objects are reachable from a hypothetical commit. And we can add new bitmaps on top of those corresponding to newer MIDX layers that we've overlaid on this existing one. You can see here there's a couple of things I want to call attention to. One is that these bitmaps from newer layers can refer to and describe the reachability information of objects from older layers. That's those first 8-bit columns that are repeated between the two layers. I also want to note that the newer layers can describe information about newer objects as well. You can see that there's 4 extra bits hanging off of the right. Those are objects that appear, let's say, in the newer layer, but not yet in the older one. And because the ordering is consistent across layers, we can just sort of conceptually read the existing bitmaps by padding them on the right with zeros and combining them in all the natural ways. And you can repeat this as many times as you want. Here I'm adding yet another layer on top, and then I'm padding them all out with some zeros as necessary. So these properties allow us to do something that I'm calling MIDX compaction. That's really important for this repacking strategy. One of the goals with having multiple MIDX layers is that we can alter earlier layers in certain limited ways without needing to rewrite any layers on top. And what's important here is that the bitmap order for incremental MIDXs is concatenated across those layers. So as long as we preserve that order whenever we do these modifications, we can perform sort of any operation that we want without having to rewrite any layers on top as long as we maintain these invariants. So to show you what I mean, here's that example from earlier. I have a 3-layer MIDX chain. And let's say that this is maybe part of some much longer MIDX chain, and I'm worried that it's getting a little bit too long and I want to compact it to have fewer layers in order to accelerate my object lookups. I can do that really easily by just combining these two older MIDX layers, into one, preserving the packs in the same ordering, and updating the chain file to reinterpret the order that the two MIDX layers form in the overall MIDX chain. From the topmost layer's perspective, nothing's actually changed. It can't tell that the bottom layer has changed beneath it because all of the objects and packs and bitmaps corresponding to them appear in the same order. So during compaction, we preserve the existing packs and the bitmap order of the objects for packs in the compaction range. And so what can we do with that? Now that we have incremental MIDXs and MIDX bitmaps, how can we combine those with the ability to compact adjacent MIDX layers to develop a new repacking strategy that solves these problems that I alluded to earlier? First, I want to start with what our goals would be for such a repacking strategy. The thing that we most want to be able to take advantage of is the ability to extend the MIDX chain without having to collapse into an all-into-one repack, no matter how large your repository is. But we want to do that without making the chain ever too long, because if we have a really long MIDX chain, we're going to run into the same object lookup performance problems that we dealt with when having many pack files. And one nice property that you might want here is that, say, newer layers in the MIDX chain might have more smaller packs on average, and older layers might have fewer larger packs. And so one way you could sort of organize these layers is to borrow an idea from geometric repacking and say that the MIDX layers have to form a geometric progression on object count across each layer in the chain. So how do we accomplish that? Here's one way to do it. This is what I've been working on over the past few months, and I'll talk a little bit about my plan to sort of get this in the hands of the open source project shortly. But conceptually, this is how you achieve those properties. The first thing you do during a maintenance operation is you repack every non-MIDX pack in your repository using a plain old geometric repack like we described earlier. As an optional step, if the newest or topmost MIDX layer in your repository contains more than some threshold number of packs, here I'm going to use 5 for my examples, we'll consider all of the packs in that layer candidates for repacking as well. Once we've performed that geometric repack, we're going to write a new MIDX layer that contains the results of that geometric repack. And if that touched one or more packs in the sort of previous newest MIDX layer, we'll go ahead and replace that layer with the newer one. Otherwise, we'll append a new layer on top of it in the chain. Finally, we're going to perform a compaction pass to combine groups of adjacent MIDX layers together in order to restore geometric progression by object count across those layers. So what does this get all of us? It gets that the compaction process ensures our MIDX chain doesn't ever get too long. Compaction encourages shorter and shorter MIDX chains. Occasionally, repacking the packs in the newest MIDX layer ensures that no MIDX layer ever contains too many packs. It encourages smaller packs per layer. And in general, we get older layers that have fewer packs with more objects, and newer ones contain more packs with fewer objects. So let's take a look at a little bit of an example. Here I have a MIDX chain with 5 layers. Older ones are at the bottom. The individual green squares within the MIDX layers represent packs, and the numbers within those squares represent the number of objects in each pack. So let's say that I'm receiving some pushes to the repository. Here they're represented as packs in this sort of staging area. Whenever it's time to do maintenance, I'm going to lay these things out in ascending order of object size, and then I'm going to perform a geometric repack over those packs. In this case, the geometric repack would produce one pack containing the sum of all 5 of its inputs, and we're going to write a new MIDX layer containing just that pack, and then clean things up a little bit. Now that we have this new MIDX layer on top, we're going to perform our compaction pass. So we're going to compare these top 2 layers and say, does MIDX layer 5 have more than half the number of objects in MIDX layer 4? Here it does, so we can combine those 2 together, and then we'll repeat as we go further and further down the chain. When we compare MIDX layers 4' against 3, we don't meet that condition, so we're done. Let's take some more pushes and see what happens as we evolve this over time. So here I'm going to simulate 5 more pushes in the repository. And again, I'm going to lay those out in ascending order. We'll do a geometric repack just like before. And here, we actually didn't need to repack all of the packs in order to ensure that we have a geometric progression. We only needed to combine the smallest 4 packs. So in doing so, we're going to write a new MIDX layer containing the result, clean things up a bit, and perform another compaction pass. We compare the top 2 layers, realize that we can compact those, and repeat further and further down the chain until we get to this state where MIDX layer 1' has fewer than half of the number of objects in MIDX layer 0, so we can't compact those, and we're done. I want to show what happens when we take one more round of pushes between maintenance operations. So I'm going to accept 5 new packs into the repository. And I'll lay those out again in ascending order, but you're going to notice that I've left a space here because the topmost MIDX layer here, MIDX layer 1', contains more than 5 packs. So all of its packs too become geometric repacking candidates. So I'll go ahead and clean things up and then lay those packs out. And when we perform a geometric repack over this much larger set of packs, we still get 1 pack out. That's what's necessary to preserve the geometric repacking condition. So I'll write a new MIDX layer containing that pack. And then because all of these packs, which happen to come from the earlier MIDX layer, got repacked as a result of the geometric repack, we're going to delete that layer and move the new one that we wrote just on top before we clean things up again. Finally, we'll do a compaction pass, realize that we can't quite merge these 2 layers together, and so we're done. So let's talk a little bit about what happened there. We saw that packs moved across layers in the MIDX chain, and that objects got pushed down into fewer and fewer packs among older layers, and those older layers survived in the repository for longer. That's really important because modifying older layers costs more I/O cycles as a result of them being larger than it does to modify newer layers. Our compaction condition ensured that MIDX chains never grew too long, and in my simulations for even really large repositories, we never grew MIDX chains longer than 8 or 10 or so layers. And that's really important to ensure that we have really great performance on repositories of any size. And I want to talk about sort of how some of this work has made its way upstream and how some of it will continue to make its way upstream. When I originally started this project, I thought I would do it in about 3 parts. The first 2 parts delivered incremental MIDX support and then corresponding bitmap support for those incremental MIDXs. These were shared with the open source project a few months ago, and they've been merged and are in released versions of Git and have been for a few months. When I started working on part 3, I realized that part 3 sort of needed to be broken up into its own few components. Part 3.1 is just a sort of code cleanup pass that I sent to the list yesterday. Part 3.2 is going to introduce the compaction routine that I demonstrated a few slides ago. And part 3.3 is going to tie all of that together to deliver this really incremental MIDX-based repacking strategy that works on repositories of sort of any size. And after these series land, I have some more ideas that I think will improve the area further, but I haven't quite yet had a chance to prototype. One idea that I think is really compelling is a sort of reachability-guided geometric repacking. When we talked about geometric repacking earlier, it was fairly naive and only really considered the number of objects in each pack in the geometric window. if we could teach geometric repacking about which objects were reachable or not, we'd be able to emit these small cruft packs to avoid storing unreachable objects in the main multipack index. And we could combine that with a feature I worked on earlier this year that allows us to combine cruft packs below some size threshold to ensure that we never got too many cruft packs outside of the MIDX. Another thing that we might consider doing is this sort of best effort garbage collection thing. Right now, when you ask Git to do a garbage collection operation, it produces an exact result. Every object that's unreachable in your repository is removed, and every object that is reachable is preserved. And that's really important when you want to remove, say, sensitive data from your repository. But if you just are more interested in sort of cleaning up the repository where you can, or trying to reduce its size, you could imagine implementing a sort of lower or best effort garbage collection operation that would leave objects in the MIDX that were unreachable to minimize the repacking effort there. You could even consider going a little bit further by performing targeted rewrites on packs that are in the MIDX to indicate tombstone markers where you removed objects. But I think that one might be a few more Git merges away before I'm ready to talk about it. Lastly, I want to explore the idea of what I'm sort of calling unitary MIDXs. As we saw in the example earlier, some of the older MIDX layers contain as few as just one pack. And so having a MIDX layer that just contains one pack isn't all that useful. In fact, all the information in the MIDX is redundant with the pack index. So we might want to consider detecting when that's the case and having the MIDX delegate its sort of object lookup queries into the single pack index to avoid duplicating the same information on disk. So what I want to illustrate here is that I believe these techniques are going to enable us to meet the next era of repacking and sort of pave the way for significantly larger repositories. All this work has been contributed to the open source project, and so you're able to run with the same tools that are powering GitHub's repacking on the world's largest repositories on your own laptops. And with that, thank you very much.